Hello learners and welcome to my YouTube channel Chemistry Unfolded. Today we will be completing the entire chemical kinetics chapter. In the video coming later to this chapter, we will be solving a lot of problems. So in the previous video, we have studied about the basics, the introduction and the zero and the first order reaction. Today we will study the second order and the remaining part. A reaction is called second order when we deal with two reactants. Okay, and the expression is given by K2 is equal to X at A minus X, where A is the concentration of your reactant. A minus X is the concentration at time T, and T is your time. Okay, so your expression is like K2 times T, which is equal to X at meaning AT, A minus X, where A minus X is your concentration at time T, A is your initial concentration, T is your time, and X is the how much concentration has been consumed. T half is given by 1 upon AK2 and T1 by 4 is given by 3T half. T completion is given by 9T half. These are the simple formulas that you have to know. In the previous videos, I've already shown how to get your T half, T1 by 4. If you have not watched the previous video, please do watch. I'll share the link in the description of this video. Now, we have studied the all the formulas for zero order, first order, second order. But if you want to find for any other order besides this, or even for second order for that matter, you can remember these general formulas. If you remember this general formulas and if you substitute that particular order number, you will get the formula. You will get your formulae. Like for example, if I say second order, I just have to replace n by 2 everywhere and I get my value. So also for T half, if I replace my n by 2, I get my values even for T half. But it is very important to note that you cannot use this formula for n not equal to 1. Okay, for 1 you cannot use it. That is the only thing. You can use it for zero order, you can use it for second order, you can use it for third order and so on. But you cannot use it for 1. That's it. You need to remember. Make sure that you learn these formulas. Okay, n times T is equal to 1 upon n minus 1 bracket 1 upon A raised to X raised to n minus 1 minus 1 upon A raised to n minus 1. Mind it, this is raised to. Similarly, for T half, 2 raised to n minus 1 it is. It's like this. 2 raised to n minus 1, then minus 1 upon n minus 1, A raised to n minus 1, Kn. Your n is the order for what you are finding the equation. Similarly, for T half, the formula is it is raised to n minus 1 divided by n minus 1 A raised to n minus 1 Kn. Moving ahead, we have the Arrenhius theory of gases. These are the 3 very important formulas that you have to know. If you do not know anything from this part, these formulas will help you out throughout. Maybe to solve problems, to plot the graphs. First formula, K is equal to A e raised to minus Ea upon RT. If I take ln of it, it will become ln of K is equal to ln of A minus Ea upon RT. And you have this, if you have two different temperatures, then your rate constants at two different temperatures will also be different. So you have ln of K2 by K1 is equal to A upon R bracket 1 upon T1 minus 1 upon T2. Coming to the graphical representation, if I want to plot a graph of K versus T, so my graph looks somewhat like this. So you have my K and here's my T. So the graph is this way. This is the graph of K versus T. Okay. Next up we have the graph of ln of K versus 1 upon T. The graph to this is given this way. On the y-axis I have my ln of K. On the x-axis I have my 1 upon T. Okay. This is my graph. For this graph we use this particular equation. This particular equation is used for this graph, wherein you get your slopes and your intercept as well, where your intercept is ln of A, that is this part is your intercept, and your slope is minus A upon R. This is your slope. Now going ahead with effect of catalyst on Arrhenius equation, we have to know a graph for this. Say suppose you have a reaction proceeding from A to product P, and as it proceeds, this is the profile it shows. Over here you have your energy on the y-axis, and here you have the reaction coordinate. So your reaction proceeds from here to your product P, and this is the profile when you do not have a catalyst. This is your transition state, and this is your reaction without catalyst. But say suppose now in my reaction I introduce a catalyst, my reaction will proceed this way. It will have a lower transition state and it will come to the product at a faster rate. So this is the one with catalyst. Is it understood? So we know that with the catalyst the reaction proceeds at a faster rate. Also you need to remember all the properties that a good catalyst shows. Coming ahead with potential energy curves, this potential energy curve shows the graph for endothermic and exothermic reactions. Here I am plotting the graph for endothermic reaction. So here is my energy. On the x-axis I have my reaction coordinate, and my graph looks somewhat like this. Endothermic reaction meaning heat is absorbed. So here is my reactant and here is my product. Fine. This is the graph for endothermic reaction. Please don't mind the handwriting. I know it's dirty because I'm using a pen on the screen, so it becomes a little problematic. Coming with exothermic reactions, the graph looks like this. Same way you have your energy here, and here is the reaction coordinate. This is the structure of the graph. Then the graph looks like this. Here is my product P, here is my reactant. Here the heat is given out, which is denoted by a negative sign. So just remember this graph. In case they ask you, If they plot certain graphs and ask you to identify the graph showing endothermic behavior or the exothermic behavior, you can identify easily like this. Thank you. Happy learning.